Our solar system is a familiar place. We know the sun and the 8 planets. But what if a giant hidden world lurks in the cold, distant shadows? This is the mystery of Planet 9. For years, astronomers have debated its existence. It is a hypothetical planet, a ghost in our cosmic backyard. Some scientists are convinced it is out there, while others remain skeptical. The search for Planet 9 is one of the most exciting quests in modern astronomy. The idea of a 9th planet, beyond Neptune, is not entirely new. But the current hunt gained serious momentum in 2016. Astronomers Mike Brown and Konstantin Batygin from Caltech noticed something odd. They saw that some small, icy bodies in the Kuiper belt moved in strange ways. Their orbits were clustered together as if sculpted by an unseen hand. A large, distant planet could explain these peculiar paths. This unseen object would need to be massive with a very wide, looping orbit. The unusual orbits of some Kuiper belt objects, or KBOs, hint at a larger, unseen gravitational force. Planet 9, if real, would be that force. Finding it would rewrite our understanding of how solar systems form and evolve over billions of years. The quest for Planet 9 is a testament to human curiosity. Just when the debate simmers, new clues emerge. Recently, researchers from Rice University have added fresh fuel to the Planet 9 fire. They presented compelling evidence supporting a large planet orbiting beyond Neptune. Their complex simulations model the chaotic early solar system. Results suggest planets like Planet 9 are a natural outcome. Led by Andre Isidoro, the team suggests a 40% chance of its existence. This new evidence has stirred the astronomical community. So how do we find this elusive world? If Planet 9 is out there, it is incredibly faint and far away. We need a very powerful eye to spot it. Enter the Vera C. Rubin Observatory. This is not just another telescope, it is a groundbreaking facility. Scientists, including the Rice University team, believe it holds the key. The Rubin Observatory is poised to revolutionize our view of the night sky. Its primary mission is to conduct a decade-long survey called the Legacy Survey of Space and Time, or LSST. This survey will map the entire visible southern sky repeatedly. The observatory is strategically located atop Cerro Pachon, a mountain in Chile. This high-altitude, remote location offers some of the clearest skies on Earth. Minimal light pollution and stable atmospheric conditions are crucial for detecting extremely faint and distant objects. The Rubin Observatory's systematic scanning of the sky will cover the regions where Planet 9 is predicted to be. It will do so with unprecedented depth and speed, looking for faint movements against the backdrop of distant stars. The Vera C. Rubin Observatory represents a monumental leap in astronomical capability. If Planet 9 is lurking in the predicted regions of space, the Rubin Observatory is our best bet to finally bring it out of the shadows. The cosmos awaits its close-up. What makes the Vera C. Rubin Observatory so special? At its heart lies a true technological marvel. It houses the largest digital camera ever built for astronomy. This camera is about the size of a small car and boasts an incredible 3.2 gigapixels. This immense resolution allows it to capture vast swaths of the sky in exquisite detail. Each image will be so large that it would require hundreds of high-definition televisions to display it at full resolution. The camera is just one part of an impressive system. The observatory also features a large 8.4-meter primary mirror. This mirror collects faint light from the distant universe. The telescope's design allows it to scan the sky rapidly. It can image the entire visible southern sky every few nights. This rapid cadence is crucial for detecting moving objects. By comparing images taken on different nights, astronomers can spot these subtle movements. The sheer volume of data the Rubin Observatory will produce is staggering. It is expected to collect about 20 terabytes of data every single night. The search for Planet 9 is just one exciting aspect of its mission. The Rice University team didn't just guess about Planet 9. Their confidence comes from looking back in time. They used powerful computers to simulate the birth of our solar system. Imagine the early solar system, not as the orderly place we know today, but as a chaotic, turbulent environment. Young planets were still forming, giant planets were migrating, and gravitational forces were flinging material around. These simulations are like cosmic history lessons. They help us understand how our planetary neighborhood came to be. They reveal the processes that shaped the worlds we see, and perhaps the ones we don't. The researchers ran thousands of different scenarios. Each scenario started with slightly different conditions for the early solar system. They watched how planetary systems evolved under these different conditions. A key finding emerged from this digital exploration. The creation of wide-orbit planets, like the hypothesized Planet 9, is not an unusual event. In fact, it seems to be a natural consequence of the early chaos. These distant worlds are like fossils from that turbulent era. The simulations showed that during the early stages, giant planets can scatter each other. One planet can give another a strong gravitational kick. Sometimes this kick is enough to eject a planet from the solar system entirely. But if the kick happens at just the right moment, the planet might be thrown into a very distant, elongated orbit. Let's dive deeper into this idea of planetary scattering. Imagine young giant planets like Jupiter and Saturn, or even Uranus and Neptune moving through the early solar system. Their gravity is immense. When they pass close to each other, they can profoundly affect each other's paths. Andre Isidoro, the lead author of the Rice University study, described it vividly. He said, "Essentially, we're watching pinballs in a cosmic arcade." This analogy perfectly captures the dynamic and somewhat random nature of these early interactions. During this chaotic dance, some planets can be flung far away from their initial birthplaces. A smaller planet, perhaps an ice giant similar to Uranus or Neptune, could find itself on an escape trajectory. In many cases, such a planet would indeed be ejected from the solar system. However, the simulations from the Rice team show that ejection is not the only fate. If the conditions are just right, the planet can be pushed into an extremely wide orbit. It remains bound to its parent star, but at a tremendous distance. The gravitational influence of nearby stars in the Sun's birth cluster could help to stabilize the wide orbit. This creates a wide-orbit planet, a relic of that early dynamic phase of our solar system's history. The strongest indirect evidence for Planet 9 comes from the Kuiper Belt. What is the Kuiper Belt? Imagine a vast, icy junkyard beyond the orbit of Neptune. It is a donut-shaped region filled with countless small, frozen bodies. These are remnants from the formation of the solar system. Pluto is one of the most famous residents of the Kuiper Belt. For a long time, we thought it was a relatively calm, orderly place. But closer observation has revealed some very strange behavior among some of its inhabitants, known as Kuiper Belt objects, or KBOs. Astronomers noticed that a handful of the most distant KBOs share peculiar orbital characteristics. Their orbits are not random, they are clustered together in an unusual way. This kind of alignment is highly unlikely to happen by chance. It strongly suggests that some unseen gravitational force is shepherding them. A massive planet, perhaps 5 to 10 times the mass of Earth, orbiting far beyond these KBOs, could explain their strange alignment. Its gravity would act like a cosmic shepherd, gently nudging these smaller bodies into specific, coordinated paths. The Kuiper Belt is not just a collection of icy rocks. It is a dynamic region holding clues to the history and structure of our outer solar system. Planet 9, if it exists, would be the source of this gravitational influence. If Planet 9 is out there, what might it be like? Based on its gravitational influence, scientists sketch a profile of this unseen world. Likely a substantial planet, 5 to 10 times Earth's mass. A super-Earth or mini-Neptune, smaller than Jupiter, larger than Earth. Its orbit is highly elongated, varying dramatically in distance from the Sun. The discovery of Planet 9 would be a monumental event. It would not just add another member to our solar system's planetary roster, it would open a brand new window. A window into the architecture and evolution of planetary systems, not just ours, but throughout the galaxy. Finding it would confirm that our solar system, too, experienced the chaotic scattering events seen in simulations. It would show that such distant, massive planets can indeed form and persist. This has profound implications for how we understand planet formation as a universal process. The research from Rice University suggests that wide-orbit planets like Planet 9 might be relatively common. They estimate that there could be one such wide-orbit planet for every 1,000 stars in the galaxy. If this is true, then there are potentially millions of Planet 9s orbiting other stars. Studying our own potential Planet 9 would give us a nearby laboratory. We could learn about the properties and origins of this class of planets. This knowledge would then inform our search for similar worlds in distant exoplanetary systems. Ultimately, The search for Planet 9 is part of a larger human endeavor. We seek to understand our place in the cosmos. The prospect of unveiling this secret world is thrilling